Hello, we're Group 41 with the Aether Sensor Network. I'm Paul Wood. Our team members are Ian Wallace, Park Benjamin, and Randy Alvarez. Our motivation for this project was to create a device that would assist those that are sensitive to negative changes in outdoor air quality. We hope to provide a solution that was cheaper than existing solutions. Finally, we were motivated to create a device to estimate the outdoor air quality. In terms of the goals for this project, we aim to create a device that can detect air pollutants, estimate the AQI, and send data wirelessly to the remote server. Additionally, we wanted to have the device be able to operate on both solar power and battery, with a solar panel charging the battery with surplus energy.
For our project objectives, we wanted the Aether node to be both low cost and lightweight. It was also important that the Aether node be able to function without much maintenance from the user. In the same vein, it also needed to be easy to install. A critical objective for the Aether node is that it could communicate sensor data it collected over LoRaWAN. And finally, we created an objective to use a website as the primary user interface. This website would need to display the data collected by the Aether node. Now we will go over the requirements we set for our design. We set the 3 requirements that we found to be the most critical in order to meet our objectives as the demonstratable requirements. This included calculating the AQI to within 25% of the EPA's reported value, drawing an average power of less than 100 milliwatts, and automatically taking a sensor reading every 15 minutes. The major constraints that we had for this project were time and money. Starting from Senior Design 1, we will have had only about 6 months to complete the entire project. We are also self-funding our project, and therefore we did not want to spend any more money than was necessary. Finally, we wanted to make sure that our project did not get too complex, such as by slowly adding too many additional features. Doing so could compromise our ability to stay within our time and money constraints. Here, you can see the overall block diagram for Aether. Starting from the left, we see the 5 primary sensor readings that Aether collects, and the arrows show the sensors that measure them. The 3 main sensors, the ZMOD 4510, BME 688, and SPS 30 are all controlled by the firmware running on the LoRa E5 microcontroller. All of these components are powered by our power subsystem. Additionally, we can see how the external battery and solar panel interface with the power system. Continuing on, we see how the LoRa E5 transmits the sensor data it collects over its antenna through LoRaWAN. Moving on to the server and web application component of the Aether network, we are using the thing stack for our LoRaWAN network and join server. This authorizes and further routes the packets received from the Aether node to our backend. The backend processes the data and then publishes a live data feed to our website.
In this section, we'll be talking about the hardware and power in the system. The overall schematic can be seen in this slide. From left to right, you can see the solar panel and USB power inputs connecting to the charge controller, with the USB-C circuit also interfacing with the USB to UART IC. On the right side, we see the 3 sensors connecting to the LoRa MCU, in addition to the SOLED programming header.
During our initial power calculations, the max current used would come out to be 244 milliamps while the device was in use. However, during sleep mode, the device would use approximately 18.45 microamps. This leads us to calculate that with a 2000 milliamp hour battery, while taking measurements every hour, our system would survive 2 months on a fully charged battery. When it comes to actual power usage, we must use a series of measurements to capture the moments when the device is in use over an extended period of time to get a better grasp of the real power requirements. This way we can see how well our calculations measure up to the real power consumption. Here you can see the average battery voltage, the range of the current, and its average, as well as the average power consumed. From this we can calculate that the battery could support the system over a period of 5 days without aid of the solar panel. This shows that our initial calculations were far off. We determined this to be because we were under the assumption that we could collect sensor data for a much shorter duration than we actually could, thus keeping the device running at full power longer than anticipated. In this slide, we have an example of how the solar panel will power the system. The measurements indicate that the solar panel is charging the battery and powering the system at the same time, with enough current to sufficiently recharge the battery to last through any downtime the Aether node may encounter, for example, cloudy days or during the night. With 183 milliamps going to the battery, we could charge the battery in just over 10 hours, while the battery would need to take 5 days to deplete completely. When it came to the solar panel, we wanted three things: high efficiency, small size, and low cost. When it comes to the selection we had, there were very few requirements. First, the range of the solar panel's input voltage had to be roughly 6 volts for the charge controller. Second, we needed a solar panel roughly the size of the unit, 9 inches by 5 inches. From here, our options were narrowed down until we found the two units shown. The P105 was chosen due to a lower cost, its input voltage more closely aligned with the charge controller, and its higher current supply that would provide more power to the unit. When it came to charge controllers, we had a few requirements that any chosen charge controller had to fulfill. First, the controller must accept dual power input lines to accept power from both a USB connection and a solar panel. Second, the chargers must have built-in circuit protections and timers to ensure the battery would not be charged under hazardous conditions. Finally, the chargers must be capable of powering a load while charging the battery at the same time. When it came down to selecting the charger, in the options we had left, the MCP stood out for several reasons. First, its capability of functioning with as little as 0.3 volts made it a prime candidate, as it would still operate even in less than ideal conditions. Second, its fast charge rate supplied a range of current that better matched our power requirements. Finally, its lower leakage current was the final reason we determined this to be the best selection for the Aether node. When it came to battery selection, the first decision we had to make was battery chemistry. Our group decided to go with lithium ion to have a more steady voltage and current as the battery discharged, a higher charge density, and a longer service life. Once we've determined the desired battery chemistry, our decision comes down to voltage, capacity, and cost. For its cost, our battery provides a great capacity in the size range we desired with the desired battery voltage. As a result, the LP103454 was selected. For the linear dropout regulator, the first thing we needed was a part that fulfilled our design constraints. The first constraint was an output of 3.3 volts to match our components, namely 2 sensors and the LoRa. Next, the output amperage must match the power requirements of about 150 milliamps. Finally, the input voltage range must match the 4.2 volts that the MCP would be outputting. From here, our selection came down lastly to cost and availability. The LP2985-3.3 fulfills all of our requirements while being available for the lowest cost, making it the best choice for our project. Finally, we needed a component capable of boosting our voltage to 5 volts in order to power our SPS30 particulate matter sensor. Like with the linear power regulator, the top requirements considered were a correct output voltage, suitable input voltage range, and correct output current. However, from there, rather than just choosing based on price and availability, a design choice has skewed our priorities at this point. It was noticed that the power drawn to the SPS30, even during sleep mode, was unusually high, so as a result, we wanted to find a boost converter with a shutdown feature. This would make the SPS30 consume no power during sleep mode, saving our battery life and lowering our power requirements. As a result, the LTC turned out to match all of our requirements, in addition to having a shutdown feature at a reasonable price, making it the clear choice.
In this slide, we see the power subsystem block diagram. The lithium-ion battery powers the system and is connected to the charge controller. To charge the battery, we have two options, either through a USB-C 5-volt input or through a solar panel input, making the system fully off-grid operational. If a secondary power input is present, the charger IC uses this input to meet the system load requirements while also powering the battery. This load-sharing feature maximizes the life of the battery by preventing it from constantly charging and discharging. Because solar panels can be unstable, they can cause the charger to constantly turn on and off. When the solar panel is connected, this charge controller incorporates its voltage proportional charge control feature to monitor the voltage of the solar panel while charging the battery. If the panel voltage drops below 4.5 volt threshold, the charger automatically turns to the battery to power the system, while allowing the panel voltage to rise again. When the USB-C input is connected, it powers the system and simultaneously charges the battery. The output of the charge controller is connected to the low voltage dropout regulator. This LDO takes the output and drops it to a constant 3.3 volt, which will be used as the main power rail in the system. The 3.3 volt then powers the microcontroller and the BME 688 as well as the ZMOD 4510 sensor. The battery is directly connected to a 5 volt boost converter with a shutdown pin. This boost converter powers the PM sensor that operates at 5 volts and can be shut down by the microcontroller to activate a low power mode. In the top left, we have the solar panel circuit with the large 4.7 microfarad capacitor to stabilize the solar panel with a reverse diode in place to prevent any leakage from the capacitor. The bottom left shows the USB to UART circuit. Because the MCU cannot communicate directly via a USB interface, a USB to UART conversion IC was needed to communicate with the MCU. ESD diode protection was also added to the design to prevent any voltage spikes caused by electrostatic discharge. The charge controller circuit is equipped with LEDs that indicate 3 system statuses: power done, charging, and charge done. Additionally, a thermistor is connected to the charger, which monitors the battery temperature to ensure the battery is not charged in unsafe temperature conditions. For measuring temperature and humidity, we chose the Bosch BME 688 sensor. There were 2 main sensors considered for this function. The other was the BME 680. The internal designs for these sensors as well as the price are very similar to each other, with both capable of using an SPI and I2C communication interface. The main difference that led the team to choosing the BME 688 was the fact that it is the newest model in the BME line of sensors and included a built-in feature for metal oxide sensing. This feature allows us to program and calibrate the sensor to measure other types of gases, giving the design more flexibility in the case where another gas wanted to be measured. To measure O3 and NO2, 2 types of sensors were considered. The first was the SPEC DGS-03 sensor, part of the SPEC family of gas sensors. The second sensor, which was the one chosen for this design, was the Renaissance ZMOD 4510. The differences between these 2 sensors were significant in both price and design, as can be seen in the table. The SPEC sensor came on a daughter board with other components already soldered on, and it uses UART communication. Although it would have decreased the amount of effort required to solder components to the board as well as programming the firmware, it would have drastically increased cost. Additionally, the Renaissance ZMOD sensor has a selective O3 measurement that can be turned on to activate a low power mode. The sensor chosen for measuring particulate matter was the SPS-30 sensor. It takes in ambient particles through a built-in fan and operates on the principle of laser scattering to detect particulate matters of varying diameters. Although the SEN54 offered additional features such as temperature, humidity, and box sensing at a lower cost, we were unable to purchase the SEN54 due to it just releasing around the time we were designing our system and ordering parts.
The microcontroller was one of the first components that we chose for our project. Our group determined that we wanted a modular chip to both contain a microcontroller and a LoRa module. Therefore, we settled on looking at LoRa modules as we wanted to avoid a second IC for the LoRa transceiver. After looking at a variety of options, we narrowed our decision down to 5 modules: the Midtronics Windy, the microchip, the RAC 4600, the OneThinks Core, and the Seed LoRa E5. Probably the most significant factor in our decision to go with the LoRa E5 was the price. As you can see, it was by far the cheapest out of all LoRa modules we looked at. At a cost of only $8, this made this the most affordable option. Additionally, the dev board for the LoRa E5 was also the cheapest. The next 2 specifications were power related. Since we wanted the Aether node to be a low power device, we knew that the microcontroller we selected had to not draw a lot of power. The LoRa E5 has both the lowest transmit current draw and the lowest sleep mode current draw of only 107 mA and 360 nA respectively. Finally, we needed to ensure that the module we selected had at least a single I2C bus and a few GPIO pins. The LoRa E5 met these requirements, and due to the combination of all these different factors, the Seed LoRa E5 ended up being the best choice for our design.
This is the MCU and sensor subsystem schematic. On the top left, we have the BME 688 sensor measuring temperature and humidity. The ZMOD 4510 sensor measuring O3 and NO2 is shown on the bottom left, and the SPS-30 sensor is shown in the middle. Each sensor's serial clock and serial data pins are connected to the respective pins on the MCU. The programming header can be seen in the top middle of the schematic and is interfaced with the MCU. This slide shows the PCB routing layout. A 4-layer PCB was used. Top and bottom layers were used for signals. The second layer was used as a 3.3 volt plane and to route other power signals. The third layer was used as a ground plane. The dimensions of the board came out to be 82.5 mm by 68 mm. After the PCB was fully routed on KiCad, this 3D model was rendered of the PCB board. This slide shows a PCB photo of our design after all components were fully soldered on it.
Here you can see some CAD-generated drawings of our enclosure design. We included 4 holes on each corner of the enclosure where screws can be inserted and tightened with a nut in order to secure the lid in place. Looking at the exploded isometric view, you can see that 4 holes were created on the inside of the enclosure where the PCB is to be mounted. After printing the enclosure, we put threaded heat set inserts into these holes so that the PCB could be screwed in place. Looking to the bottom half of the enclosure, you can see two extrusions that were created to keep the SPS-30 in place. There's an additional extrusion coming from the top lid that keeps the SPS-30 from moving vertically when the enclosure is tightened shut. There are also two holes created for the intake and outtake fans of the SPS-30. Moving to the projected views on the left, you can see that holes were included for the solar panel DC jack, the USB-C cable, and the antenna. Here is a photo of the final prototype. The PCB is mounted inside, and you can see the antenna that is attached to the PCB sticking out. Here is another photo of the final prototype. In this photo, the lid is removed, and you can see how every component fits in the enclosure. The PCB is screwed in place, and the SPS-30 is held in place by the extrusions. The battery is connected and tucked into the top of the enclosure. When the lid is closed, the battery does not shift around because it is just tall enough to fit and is securely held in place. We will now go over the firmware. For the Aether node firmware, our design requires that we are able to read data from the sensors, transmit that data over LoRaWAN, perform power management for the system, and allow the user to read sensor readings from a shell. Here is a diagram showing a high-level overview of the operation of the Aether node firmware. Note that the black arrows in this diagram indicate control flow, while the red arrows indicate data flow. Starting with the sensor control flow part of the diagram, we see that all three of the sensors in our design follow the same general flow. First, the sensors start out in a sleep state. After a specified period of time has elapsed, they wake up and take a sensor reading, which is then packaged into a data packet. This data packet is then placed into a message queue. The sensor loop then returns to sleep, which brings us to the LoRa control flow, where a message gets popped from the queue and sent. We then wait for the message to send successfully. Once this occurs, we return to the first state to process another message. Lastly, the USB serial command control flow uses the Zephyr Shell API to get sensor values directly, even if the sensor is currently sleeping. Arguably, the single most important component selection we made for the firmware was the choice of RTOS. We knew from the beginning that we would need the additional features of an RTOS over simply doing bare metal programming. In the early stages of our firmware development, we were using the STM32 Cube IDE that came with example projects using FreeRTOS. However, we quickly found the STM IDE to be slow and cumbersome. Eventually we came across Zephyr RTOS. Zephyr is an open source RTOS maintained by Nordic Semiconductor. One of the things about Zephyr we liked was the use of command line tools. This allowed us to use the text editor of our choice instead of a clunky IDE. As you can see in this table, it had built-in support for features that we knew we would need, such as a user shell and power management, things that FreeRTOS did not support out of the box. Additionally, the device tree model for developing device drivers proved to be easier to work with after some learning than working directly with the STM-provided HAL. Zephyr also included LoRaWAN support for the LoRa E5, which was definitely a requirement for us. Finally, even though the average file size of compiled Zephyr binaries was larger, the LoRa E5 had enough flash memory that it didn't really matter. These contributed to our decision to go with Zephyr. Here, we show how we formatted our sensor data using the Cayenne LPP format. Packets were sent over LoRaWAN using this format. Cayenne LPP is designed to be minimal and use a small amount of bytes. A single Cayenne packet starts with a channel byte. This indicates what sensor the packet is from. Next, there is a byte to indicate what the data type of the packet is, such as temperature. Finally, there are N bytes for the payload. The receiver of the packet will know how many bytes to read based on the channel and type bytes. We implemented some power management for the Aether node to increase the overall battery life of the device. The first method was to turn off the SPS-30 when it is not taking measurements, since it has the highest current draw out of all of our sensors. The second method was to put the MCU into a sleep state, known as Stop 1, when no sensor measurements are being performed. We were unable to implement the lowest low power mode, since it was unable to be used through Zephyr. In order to use it, we would have had to use the lower level HAL drivers.
In order to effectively view the various types of data generated by the Aether node, we wanted the website to have visualizations that were clear and precise. We wanted users to easily choose the type of data or layer they wanted to see, along with historical values. Users should be able to see the readings generated by their devices and view their device on the map. Also, since air quality is generally useful, we wanted the data readings to be publicly available but anonymize the user-specific information. Lastly, since users are not going to be constantly glued to our website, we wanted users to be able to configure alerts for when a certain threshold was met. Here shows the different backend services we considered. Initially, only Azure and AWS were considered for reasons I'll shortly describe. Our backend requirements are simple. We need to host a website, store data in a database, and have some medium to run code. Ideally, we would like services tailored towards IoT and LoRaWAN. Azure and AWS are both very similar and offer about the same services. Because of AWS's LoRaWAN service, IoT Core for LoRaWAN, we decided to go with AWS. However, AWS was not our final choice for backend services. While they do provide a vast amount of services with ample documentation, it proved to be costly in terms of time and money. It was slow to iterate on, as deployments took 10 to 20 minutes to complete. Also, there are many gotchas with using AWS, such as requiring NATs to have Lambda functions access the internet, which have hourly and throughput costs. This is why we decided to move to Supabase, a pre-configured custom PostgreSQL database. Supabase allows us to use their custom JavaScript client to access the database using REST. They also provide the ability to perform HTTP requests within Postgres itself, along with programming database functions in JavaScript through the Postgres extension. This means that we can write all of our application code in a database. Another plus is that their payment tiers are based on storage, not data traffic. As we'll talk about on the next slide, we'll use the Things stack to act as our LoRaWAN network and join server instead, which is simpler to use than AWS's. The Things stack is a public and private LoRaWAN backend service that simplifies getting device messages to and from an application. They provide integrations for Azure, AWS, MQTT, and webhooks, which is what we used. Furthermore, they provide a REST API for interacting with their various services for managing and configuring devices, gateways, applications, and access control. As for the front end, we initially considered these three frameworks: React, Vue, and Angular. All are moderately popular, which is important for dealing with design best practices and online support. It is because of the vast continued updates, support, and popularity that we decided to go with React. Our objective is not to create a front-end application from scratch, but otherwise provide a companion application to interface with the Aether node using trusted, well-known libraries within reason. Here shows our use case diagram. Visitors, who are people who do not have an account, can register, view data, and interact with the map. Users of the application, who are people who do have an account, can log in, configure and modify alerts, add and modify their devices, and view device-specific information. Email alerts are sent to users using MailerSend, which is initiated by Supabase. All mapping services are provided by Mapbox. This shows our stack design. Supabase is at the core of everything. It acts as our API and database. However, AWS still hosts our website and domain certificates. All of our code is automatically deployed through GitHub Actions. On this slide, you can see a screenshot of our website. The sidebar on the left shows the different layers users can view. Below that, users can view and add devices. By clicking the name, they can bring up details about the device, as you'll see on the next slide. The top right shows a legend of the current layer. Here shows the device details, where users can view metadata, edit parameters, view event logs, and real-time and historical data for that particular device. Here shows one of the pages on the user dashboard where users can view and create alerts. Alerts are created for a particular device, as you can see from the drop-down menu, and a layer to be triggered at a specific threshold, whose UI is not shown because of the drop-down menu.
This slide shows the hardware challenges faced during this design. Initially, the charger would not charge the battery. After doing more research, we found that the battery we were using, a 3-cell lithium-ion battery, was not compatible with the charger, and we had to use a single-cell lithium-ion battery instead. The next problem we ran into was the power rail in the PCB got shorted and some of the components were damaged. A new PCB had to be used and the damaged components had to be replaced. Another problem we ran into was the 3.3 volt LDO stopped outputting the 3.3 volts. After troubleshooting the board, we found that cold solder joints were the issue, and after reheating, this fixed the issue. The last problem we faced with hardware was the charger would not charge the battery. Again, so this problem ended up being the thermistor was faulty and was giving extremely high resistance values, causing the charger to stop charging because it was detecting an unsafe charging state. A new thermistor solved this problem.
We had many challenges when developing our firmware. One of them was working as a team and organizing our Git workflow, which required us to learn more about Git. Another was getting power management to work, which was solved by lots of trial and error along with reading the Zephyr API and source. As for the backend, to host a website there are multiple services you have to learn, and they can be a huge hurdle, so take it one step at a time. Lastly, making sure everything was working end-to-end was difficult, so I implemented some testing scripts to fuzz input values into the uplink handler in the database.
In this section, we'll be covering administrative content. One of the goals we had was to have a unit cost less than $250 to keep our operating costs low, which was accomplished. The two largest expenses we encountered were the components placed on the PCB as well as the cost of the SPS sensor. We were able to bring the cost down by sourcing most of our parts from a single vendor. Additionally, the enclosure was able to be 3D printed for free, making the only expenses related to the enclosure come from the cost of the screws needed to keep it closed. Here you can see the overall progress of the project. Currently, we have a fully functioning prototype in all aspects. On this slide, you can see how we chose to distribute tasks throughout our time working. We tried to ensure each team member was the primary contributor on at least two aspects of the project and took up a supporting role on at least one other aspect.